Recall that we have two logarithmic bases that we primarily work with. One is base e and the other is base 10. A log in base e is written as natural log, so log base e of x is ln x, and a log in base 10 of x is just log x without the 10 having to be written. Other logarithmic bases must be written. Now, there must be a way for us to convert a log in some other base into these bases, and vice versa. That is, suppose we want to change this log in base 5 of x to log base in base 7. I can think of no reason why we would need to do that right now, but we ought to be able to do something like that, that is, change of base. Now, it turns out that it's pretty easy to do. All we need to do is manipulate this just a little bit, and I'll show you how it's done. And then we'll use what we see as a formula. We'll just use that as a template. Here's log base 5 of x. I'm setting it equal to n. And now I'm just going to take this logarithmic form and go into exponential form. It's 5 to the n equals x. All right, now let's come back to log form and let's change the base. Let's go into another base. You see, and I'm choosing the natural log idea here. So I'm just going ln on both sides, and then the n becomes the coefficient here, and then divide on both sides by ln5, and we have n as ln x over ln5. Now the n here is the n up here, and so log base 5 of x is ln x over ln5. So back over here, log base 5 of x is ln x over ln5. Now I could have chosen any logarithmic base over here. I could choose log base 7, you see, to apply on both sides of that equation. And so this changing of base can occur with any logarithmic base. I could write this as log x over log 5. You see, and I could place any base that I want to here. So this then becomes a change of base formula for us in the future. It might come in handy from time to time. Let's look at a couple of situations involving exponential equations and logarithmic equations. There are actually 4 forms that we can face when we solve these kinds of equations. And it's kind of important to get your head into the problem very quickly to realize which form you're looking at. I just want to show you, expose you to all of them. You've seen them probably before, but I want to put them all in one spot. There are 2 kinds of exponential equations that we can face. Here's one, here's the other. Now, in both cases, your first choice for solution is to try to make the bases look alike on both sides of the equation. Here, it's pretty easy to do. It's 3 to the x equals 1 over 3 to the 4th. So 3 to the x equals 3 to the negative 4. Bases are alike. Jump into the exponential world and solve. All right? But in a situation like this, and we've seen it before, we can't make the bases look alike, so we have to solve this exponential equation by using logarithms. And we've seen the routine before. We just apply logarithm on both sides and away we go. And I'll run through it right quick for you using natural logs. We could use common logs, we could use logs of a foreign base if we want to, but we would probably choose either the log of base 10 or the log base e, the natural log, because those are the ones that are in the calculator. At any rate, ln 2 to the x then is equal to ln 5, and then this is x ln 2 equals ln 5. X then is ln 5 over ln 2, and we punch the calculator to solve this. Now with logarithmic equations, there are also 2 forms, and you just jumpstart your logic pattern towards solution by noticing which form is in front of you. Here we have the log of something on both sides. And here we have the log of something on one side only and a constant on the other side. Now this doesn't have to be a constant. It could have a variable in it. But the point is we have a log of an entity here, the log of an entity over here. And that's one kind of form, and the other kind of form is where we have a log of an entity only on one side. And it may turn out that in problems like these, in logarithmic equations, we have some manipulation to perform before we get to one form or the other like this. But once we arrive at this position, the tactic that we're using is quite specific, or it can be. Here we have, since we have the log of this number is equal to the log of that number, it means that these numbers must be alike, you see. So we can immediately think of, well, there's several ways to think about it. I kind of like to think of it as we have an operation called logarithm. Let's undo the operation. Let's anti-log over here, anti-log over there, you see. And so we get that 3x equals 15, and x then is 5. Now, so that's the tactic that we can take here. There are other ways to solve this, other useful ways, viable ways to solve this. We can throw both logarithms on one side of the equation, for example, and manipulate, but this is a very fast way to deal with it at this point. Now, when the log business is only on one side of the equation, then we typically the best way to approach it is to go into the exponential form. Here this would be base exponent set equal to x. So x equals 2 to the negative 4 power, or x is 1/16 when you evaluate this. Now here's one that looks a little more complicated, and it's a logarithmic equation because it has a log in it, and we want to solve this for x. Now, if we use the tactic that we took earlier, we would go immediately into the exponential form. We would say 2 to this exponent is equal to 64. And then we would try to make the bases look alike, and we could do that. We could solve it that way. Another way to solve it is to take just the logarithm part. When both of these are numbers, this is just a number in the calculator, if you want to look at it like this, or it's a number that we can evaluate by manipulation purposes. And as a matter of fact, the very quick interpretation of this, you know, logarithms are exponents. So this number is an exponent. Just to ignore this for a moment. That is an exponent. It's the exponent on 2 that gives 64. In other words, 2 to what exponent is 64? That's what that number is. It's 6. But and if you know that, you can just make the quick replacement here that this is 6. If you don't know that right away, then what you can do is come out to the side or somewhere and do this and say, oh, let me think about that just a little bit. It is log base 2 of 64, and I'll set it equal to something like n. In the exponential form, it's 2 to the n equals 64. And, oh, happy day, we can write 64 as 2 to the 6th power. So n then is 6. N is 6. N was this business, so we can replace this with 6. So just another technique in your mathematical toolbox for dealing with a problem like this. So we could just very quickly then, after doing that off to the side, rewrite this as 6, and then 3x then equals 1, x is 1/3. Let's think, we want to return to our investigation of differentiation and integration now, and consider a problem like this. Y equals 7 to the x power, and we want the derivative of this. We want y prime. We want to figure out a way to calculate this now. We know that if y is e to the x power, then y prime is e to the x power. And even more generally, if y is e to the u, then we would have y prime is e to the u times u prime. Now there must be a way to manipulate this situation into a form where we have a base e to generate some kind of formula here or rule regarding this idea of the base of our exponential expression being different than e. And certainly that's what we're going to do. We're going to manipulate this a little bit. Here's y equals 7 to the x. In logarithmic form, it's log base 7 of y equals x. By using the change of base idea, changing it into the natural base e, this is ln y over ln 7 on this side. And then multiplying on both sides by ln 7, we get this. Now let's go back into the exponential form. It is base to this exponent is equal to y. So y is e to the ln 7 times x. And then y prime, you see this is that form of e to the u, you see, and so y prime is e to the u times u prime. So this is just a coefficient times x, and it's the coefficient. All right, so it would probably be written as ln 7 times 7 to the x power. Remember, we took 7 to the x. 7 to the x was equal to y, and then we made y equal to this. But this is 7 to the x. So we would probably replace it back to see the pattern for taking the derivative when we have a base other than e. All right. So the pattern is, now remember we started with 7 to the x. It was y equals 7 to the x. So it's ln base times what we start with. All right. Let's review just a little bit what we have had and what we now have in terms of this derivative idea. The derivative of e to the u is e to the u prime. All right, now we have the idea of the derivative of a to the x is ln base times the a to the x. You see, that's what we generated right here. And even more generally than this, suppose the x wasn't an x, but it was like an expression involving x. Well, that's pretty easy to deal with too. The derivative of a to the u is ln base, you see the natural log of the base, times what we have here, times the derivative of the u part. So it's times u prime. Very easy situation once we see this kind of pattern. And as a matter of fact, we could actually use this pattern for e to the u. Because after all, this would become ln e, which we know to be 1, you see, and then it would be the same as what we have up here. But at any rate, if we have y equals 2 to the 3x, then y prime is, well, let's see, just follow the pattern here. We would have ln 2 times what we have here times the derivative of 3x, and then we would manipulate it a little bit and probably write this as, maybe 3 ln 2 times 2 to the 3x power. Here we have y equals log base 7 of x, and we'd like the derivative here. We'd like a way of calculating the derivative of a logarithm whose base is not e. Now, it's pretty easy, though, for us to proceed here to manipulate this into a form that's familiar to us. For example, if before we try to find y prime, suppose we do this. Suppose we say that we can write y as ln x over ln 7, you see, just by our change of base. And then we have 1 over ln 7, just for emphasis here, times ln x. So we have a constant times ln x. And now it's y prime equals, now we know how to find the derivative of this, I think. Recall that, well, let's come out to the side and we'll see what to recall. Remember, the derivative of ln x is 1 over x, and more generally than that, the derivative of ln u is 1 over u prime, and usually we write this as u prime over u. But the transition from this form to this form, it's evident here. You see that all we're doing in this form is multiplying by the derivative of u, but we usually express it like this. Now, our problem over here is more related to this idea because we have an ln x over here. So let's come back. The ln x is 1 over x. That is, the derivative of ln x is 1 over x. So we have this, and we would probably consolidate matters into this kind of form. Now notice that we were taking the derivative of log base 7. This is that base that we were talking about earlier. And here's the x. So it's the natural log of the base that we have in our logarithm up here times x. So it's very closely related to this other matter. To organize things a little bit, we've looked at these two, and now we're talking about logarithms of bases other than e. So we have log base a of x, as we just saw. This is a generalized version of that, is 1 over a natural log of this base times the x. And even more general than that, we can sort of extrapolate from this that if the x is a u, then all we need to do in the same form is just multiply by u prime. So it's 1 over ln a times the u, then times u prime. And usually this is written with the u prime in the numerator, as we saw earlier. Well, let's consider a problem. The neat thing about logarithms and working with logarithms is that there are so many forms, there are so many manipulative opportunities, and we can take advantage of that in a problem like this. We have log base 3 of x, the square root of x minus 1 over 2. Now notice that in the numerator we have a product, and all of this is a quotient. So it's the log of the numerator minus the log of the denominator, but this numerator is a product, so it's the log of one factor plus the log of the other factor, you see, and then minus the log base 3 of 2. And this 1/2 by the power rule, the 1/2 can become the coefficient of the logarithm here. Now all of this could be done possibly in one step if you understand the properties of logarithms. I'm putting in all the steps here just so there'll be no confusion, but you can certainly eliminate a couple of these steps. Well, let's see, when we take the derivative now, we're taking the derivative of each of these. And so the derivative of log base 3 of x is 1 over ln 3, ln that base, times the x. And here we're using the idea of this being log base a of u. You see, we're using that form from over here. And it's u prime. Well, u prime, the derivative of this would be simply 1 over ln 3 times the x minus 1. And we just bring down the 1/2 here. Now this is a constant, so its derivative is 0, and it goes out. And we would probably just pull out the ln 3 in these denominators as a common factor, and then write this as 1 over x, and this as 1 over 2 times x minus 1. I think this would be a good time, because we have looked at so many derivative kinds of formulas, if we kind of organize the whole thing in one spot. And it would probably be a good idea if you made a list of all of these somehow. Let's look over here first. Now this goes back to the very beginning of our work with derivatives. The derivative of a constant is 0, the derivative of x is 1. The derivative of a constant times an expression involving x is the constant times the derivative of the expression involving x. The derivative of a sum or difference is the sum or difference of derivatives. And the derivative of a product, and here's where it started to get, this seemed confusing at the time, it certainly is not confusing anymore, I'm sure, and the derivative of a quotient. Now we're taking this organization up to the point of trigonometry. The trig functions are a separate set altogether, and we'll examine those a little bit later. But for right now, let's just go up to that point. Now the next item was a very, very important item. It was the general power rule, and it's the derivative of u to the n is n times u to the n minus 1 times u prime. And we are using the chain rule to generate this, or to develop this general power rule. What I want you to notice about this conceptually is that this is a variable quantity, or this is something, an expression that has a variable in it, and the n is a constant. So variable raised to a constant. Now we'll look at another form in a moment where the base is a constant and the exponent is a variable. You see, that's what we were just looking at a moment ago. So it's interesting conceptually, because to get your head into these kinds of problems, you have to know what you're looking at very quickly. And you have to identify where's the variable here, you see? Is the variable as the base of the exponent, or is it in the exponent, you see? And that kind of thing. So at any rate, then we talked about logarithms just a moment ago. So it's for the natural log of u, it's u prime over u. For a more general logarithmic base, for the log a of u, it's u prime over ln a times u. Now notice that there's the difference in these two is just the appearance of the natural log of a in this denominator. Otherwise, they are the same. Makes it kind of easy to recall these situations. Now, we had some other forms in here. We had ln x, you see, in the mix here, but we don't need to list that because if this is an x, the derivative of x is just 1, you see, and then this would be x. So there are some consolidation opportunities here in making a complete list of these. Okay, and now we talk about the exponential versions. The derivative of e to the u is e to the u times u prime, and more generally than that, the derivative of a to the u is ln a times a to the u times u prime. And we notice that there's a great deal of similarity here, the only difference, the major difference being that this ln a factor makes its appearance in the problem. Well, here's the one where we have a constant base and a variable in the exponent. And whereas up here it was the other way around. It was the variable in the base and a constant exponent. Now in this structure, in all of these rules, we don't have a situation where we have a rule for the derivative of a variable base raised to a variable exponent. But it turns out that that's pretty easy to deal with. In fact, most of the other situations that we'll be faced with at this point, we can manipulate into one of these forms. Let me show you what I mean. If we just take a simple version of variable raised to variable. All right, so here we have y is x to the x power. And see, we just pop it into the logarithmic world, and then suddenly we have both exponents and bases on the same line, and then we can deal with it. Here's how the flow goes. Take the natural log on both sides, then this ln x to the x, this x becomes a coefficient. And now we come out of that logarithmic world, you see, just in the exponential form, base e exponent here. So y is e to this exponent. Now understand, though, that e to the x ln x is really x to the x power. These are interchangeable parts here because they're both y. You see, we just manipulated this into that form. And now that it's in this form, it's pretty easy to find the derivative. So y prime then is this times the derivative of that. And it turns out that taking the derivative of this is, I don't know, marginally challenging, I suppose. We have a product here. We're using the product rule. So it's x times the derivative of this, which is 1 over x. And then it is the derivative of x, which is 1, times ln x. So we have this. Now these cancel, so this is ln x plus 1. And remember that the e to the x ln x was nothing but x to the x, so I'll substitute back, and this is the form that we get. The general idea, though, the concept here is that when we're faced with something that we don't directly have a rule or a formula for, we just manipulate it a little bit into one of the forms that we do have some information about. Let's turn attention now to integration. Recall that up to this point, we know that the integral of e to the u du is e to the u plus c. Now, another notation that's equivalent to this, that instead of writing du, we can write u prime dx. Some people like this idea, some people like that idea, but it's pattern recognition that we're looking for, and whatever form causes you to recognize a pattern easier, that's the one that you ought to use. And I hope it isn't confusing that sometimes I'll use one form and sometimes the other as I demonstrate problems here on the board. I'm just showing you alternative methods here. Another technique that's important in the way that we're going to develop the idea, and the idea that we're developing is the notion of integrating using a constant other than e raised to some general exponent. We'll use a specific exponent and then a general exponent later. But involved in that technique is that idea that we can take a number like 5 and rewrite it as e to the natural log of that number. You see, these are just equivalent, just interchangeable parts, a quick manipulation that we can make. It's easy to see this if we set 5 equal to y and then take the natural log on both sides and then just come right out of that into the exponential form. This is e to that exponent equals y, or y equals e to this as the exponent. So, and y was 5, so 5 is equal to e ln 5. All right, so with that manipulation, we can solve a problem like this rather easily. The integral of 2 to the x. Now, we know how to do e to the x, but what about 2 to the x? Well, it turns out that we can jump right into that form of e very quickly if we understand that 2 is e to the ln 2. So e to the ln 2 to the x is e to the ln 2 times x. So now we're in the form that we had before, and now it's a matter of recognizing a certain pattern. Now, if we imagine that the u part is this, is the ln 2 times x, then u prime is ln 2. Now, notice I'm using u prime and not du. See, it depends on what you want to, how you want to display it or how you want to think about it. I kind of like this form, or I'll use it in this particular case. But the u prime is ln 2, and that just means that in order for us to work this problem, we need to see the form of e to the u times u prime dx, and to meet the pattern over here. So we need an ln 2 factor in here. To get that factor in here, we'll multiply on the outside by 1 over ln 2 and on the inside by the ln 2. And now here's the pattern that we're looking for. So the integral is, bring this down, it's this times the outside fraction, then plus a constant. Now recall that the e to the ln 2 times x is just 2 to the x power. So I'm back substituting here back to this form. Now all of this just shows how a general situation of integrating a constant base to an exponent x turns out. We're not going to go through all of these shenanigans every time, because we can just, by the pattern now that we understand, we can do it very quickly. That the integral of this is that, and so we can generalize the situation into this. The integral of a to the x dx is 1 over the natural log of a, 1 over the natural log of this base, times a to the x, and then plus c. And then taking it just a little bit further, generalizing it even more, substituting for x a u idea, then we would have the integral of a to the u du, which could be, the du part could be written as u prime dx. Either of these forms is okay, but from either of those, we get 1 over ln a times a to the u plus c. So it's a very similar pattern to the one that we recognized before. The result is very similar to the result that we have here as well. Okay. Here we have a summary of our integration techniques, and we're taking this summary from sort of the beginning, and we're going through to where we are, but I'm not including the trig functions. We'll consider those as separate items later on. The integral, now these first two are just manipulative in nature. We're not actually completing an integration, we are manipulating integrals. So it's the integral of a constant times a function is the constant times the integral of the function. And the integral of the sum or difference of functions is the integral of one function plus or minus the integral of the other function. So these are manipulations. Now let's get to the true meat of the matter. The integral of du, which means the same thing as the integral of u prime dx, you see, is equal to u plus c. And I'm putting in these alternate forms here to make sure we understand that we're not talking about two different things here. We're talking about two things that are interchangeable. And I think it's important for that recognition factor to see that all in one place. All right, the integral of u to the n du, which it can also be written, instead of du, we can write u prime dx. But this is u to the n plus 1 over n plus 1 plus c, where n is not equal to -1. Now this was the general power rule for integration. And this was a very important and powerful form that we need to recognize and we've used so very many times. Now notice the caveat here at the end that n is not equal to -1, and that's because it would cause this denominator to become 0, and that would cause an undefined situation. Now we had a special definition for the situation when the n was equal to -1. Now let's backtrack through this form all the way to here. This n cannot be equal to -1. We can't have 1 over u, you see. We can't integrate 1 over u, or u to the -1. But we have the special definition for that u to the -1 du, or u to the -1 u prime dx, or the integral of 1 over u du, or you see the integral of 1 over u prime dx, which is the integral of u prime over u dx. And as I go through all of this, and it's so symbolic, it seems to be very confusing, but this is really simple stuff. It is just a manipulation of the same thing. We're churning the same idea over and over and over again. This is a form that I kind of like because I can see a pattern here of a u and its derivative, you see, in the same fraction. But at any rate, when we see this pattern, we get ln absolute value u plus c. Now we come to the point where we are right now with the integral of e to the x, and then e to the u, and then a general a to the x, and then more generally a to the u. It is the e to the u idea, e to the u du, the integral of that, can also be written as the integral of e to the u prime dx. But either of these gives us e to the u plus c. And then, from what we did just a few moments ago, a base other than e gives us an integration like this. It's just we're just adding in here, or popping in a fraction into this answer. It's very similar to the idea from above, except we have this factor of 1 over natural log of a. So it's 1 over the natural log of this base. And same idea here. The only thing is, to recognize the pattern here, we have to have, when we have a u idea, we have to have a du factor in here, or a u prime factor, interchangeable kind of parts here. But once we see that pattern, then we get the same idea that we had before. It's 1 over the natural log of the base times a to the u plus c. Let's look at some problems now that are modeled using exponential equations. A classic kind of problem is the one involving compounding of interest. Here's the formula, and you perhaps have seen this before. A stands for the amount in the account after a certain period of time. P is the principal, or the amount deposited. R is the rate of interest. N is the number of compoundings per year. Notice that N appears in 2 places here, and T is the time in years. There's also a formula that is associated with the continuous compounding of interest, and here's that formula. A, the amount in the account, is P times E to the RT power. Well, let's make some calculations here. I think it's rather interesting how money accumulates if it's invested and left in an investment over a period of time. And I'd like you to notice the difference in the amount of money accumulated according to the number of times this compounding occurs in a year. Let's figure that $2,500 is invested at 7% for 5 years. Now, if the compounding occurs annually, that's 1 time per year, then we would find the amount like this. Replace P with 2,500, replace R with 7%, or 0.07. N, the number of compoundings, is 1, and N is 1, T is 5. And now it's just a calculator push. And so punching the calculator with this information, we find that the amount in the account is $3,506.38. Let's see what happens when the compounding occurs more often. Remember now, a little over $3,500, $3,506. All right. For quarterly compounding, it looks like this, and we're going to run through these pretty quickly because, after all, we're not really using logarithmic ideas. We're not integrating, we're not differentiating. Gee, this is pretty easy stuff, isn't it? So we'll just march through right quick. For quarterly compounding, you want to write your formula down every time we use this model, and then replace the letters within the formula and then punch the calculator. But notice now the N, the number of compoundings per year, is 4 because we're talking quarterly, and 4 appears here as well. And the amount in the account after the 5-year period is $3,536.95. Now remember, for the annual compounding, it was just a little over $3,500. It was $3,506. So this is about $30 more when we're compounding quarterly. Let's see what happens when compounding monthly. We have the $2,500 now. In this denominator, we're using 12, and then 12 up here in the exponent as well. $3,544.06. Not that much more. Now what about for daily? Let's see. 2,500, the daily compounding, 365 days in the year, so 365 here, 365 here, and we get a total of $3,547.55. Notice how little difference there is here between the monthly compounding and the daily compounding. Hardly any difference at all. The biggest difference came between the annual compounding and the quarterly compounding. You see, so just compounding anything more often than annually seems to make a major difference. Well, what about for continuous compounding? Popping into our continuous compounding model, P, the principal, is 2,500. R, the interest rate, is 7%. T, the time, 5 years. And again, it's a calculator push here, and I'm going to make this calculation right quick on the fly. I forgot to put this in here. Let's see, we have 2,500 times E to the 0.07 times 5. And it's 3,500. Look how close this is. It's $3,547.67. The difference between this and this is it's just pennies different from continuous compounding versus daily compounding. Here's an interesting problem that does require us to use some of our more compelling information about exponents and so forth. It's a problem that has to do with doubling. Compounding monthly. How much time is required for an investment to double if the return is 12%? So the investment is earning 12%. Now notice the amount of principal is not written here, but it doesn't really make any difference. It doesn't matter whether the principal is $5 or the principal is $500,000. We're talking about a doubling time, and the doubling time is the same regardless of how large the investment is. And the way to deal with this in terms of the model is like this. The amount is just double the amount that we're putting in. So we're replacing now for the A, it's 2 times the original investment. Interest rate is 12%. Number of compoundings, let's see, monthly, that's 12. And 12 times T. Now T is the unknown quantity here. We're solving for T. Now notice here, if we divide on both sides by P, these go out. So we have 2 equals, now 0.12 divided by 12, that's 0.01. Add 1, and this is 1.01 to the 12t power, and we're solving for t. Now we need to, this is an exponential equation, and we need to either make the bases look alike. Not possible here, not easily possible anyway. Since we can't make the bases look alike in order to get into the exponential world, we'll use logarithms. And I'll use natural log here, so ln2 equals ln of this side. Now ln of this side means the 12t will become the coefficient of ln 1.01. Okay, I kind of skipped a step there, but when I put ln of this side, the 12t becomes the coefficient. All right, then the t is over here with this constant and that constant, so we'll divide on both sides by those two constants. to find t to be ln2 divided by 12 ln 1.01. And when we punch the calculator on this, we find out that that time required for doubling the investment is 5.75 years. Now, the big difference in this problem and the previous problem, in the previous problem, the interest rate was 7%. In this problem, the interest rate is 12%. And in this other problem, we were talking about a 5-year period, exactly 5 years. And the amount of money went from $2,500 to a little over $3,500. And so the difference here, you know, the doubling time on that would be quite a bit more than this 5 3/4 year period, because the interest rate is so much lower than the 12%. You raise that interest rate, the doubling time shortens considerably. Here's a problem that deals with timber yield. It says the yield V in millions of cubic feet per acre for a stand of timber at age T years is V, the volume, is 6.7 times e to this exponent. Find the limiting volume of wood per acre as T approaches infinity. That's what's the maximum amount of volume that we could attain even if the amount of time is indefinite. Well, what we're calculating is the limit as T approaches infinity of 6.7 e to the negative 48.1 over t. And as t approaches infinity, this fraction goes to 0. So this is approaching, or becomes, 6.7 e to the 0, but e to the 0 is 1, so this is 6.7 million cubic feet per acre. Next part of the problem says, find the rate at which the yield is changing when t equals 20 years and t equals 60 years. The rate of change at a particular time. Wow, derivative. The bell should go off, you see, about what we have to do at this point. When we see rate of change, we think derivative automatically. So we're taking this, this formula for the yield. I'm just repeating it right here, and we want to take its derivative. Think about what we have to do that. V prime is simply 6.7 e to this exponent. Now, the next thing we need to put down is, this is the u part. You see, if we're meeting the pattern that we've been talking about before, but this is the u, and what we want here is u prime. So we want the derivative of this. Now, we might be able to see through that, and then again, we might need to make some notes on the side. You know, something like, oh, over here we might do like this. We might say, all right, this is negative 48.1 over t. Well, that's t to the negative 1. And then the derivative of this is negative 1 times this. Oh, that's 48.1 t to the negative 2. And the t to the negative 2 becomes 2 squared in the denominator. So this is 48.1 over t squared. So we come back over here, 48.1 over t squared. You see, something like that is what you would probably go through when you're making the calculation. All right, so then V prime, if we clean this up a little bit, we would multiply 6.7 times 48.1. Turns out that's 322.27. And that's over t squared, and all this is times e to the negative 48.1 over t. Now, we would like to, with this derivative idea, we can find the rate of change at any point in time. So the rate of change when t is 20 would be found by replacing t in these two places with 20. I've done that up here. I've replaced the t that was here with 20 and the t that's here with 20, and then punching the calculator, I find that the rate of change after 20 years is 0.073 million cubic feet per year. That's the rate of change at that point. After 60 years, the rate of change turns out to be, now notice the 60 in the two positions for T, the rate of change is 0.040 million cubic feet per year. I was thinking to myself, gee, this doesn't seem like a very quick rate of change, and then I'm thinking, well, gee, we're talking about the growth of trees here, so we're not exactly talking about racing. But at the same time, I wondered whether or not it might be reasonable to think that a timber company would wait 60 years to cut trees. So I decided to, just out of curiosity, find out about the yield per acre after 20 years and the yield per acre after 60 years. Rather eye-opening kind of thing. This rate, although it may seem rather low, when it's, you know, that same rate is just galloping right along from year to year. It's changing a little bit, but that rate of growth, we still have growth going on, makes a big difference after a lot of years. I found that the volume after 20 years is 0.6 million cubic feet per acre. And then just popping in a 60 into the original formula for volume, it turns out to be 3 million cubic feet per acre if we're able to wait 60 years before cutting the timber. Quite a bit of difference here, waiting 20 years versus waiting 60 years. Here's a problem involving a fish population. It says a lake is stocked with 500 fish and their population increases according to the logistics curve P of T equals and all of this, where T is measured in months. All right, so the population according to time is this. You might, you know, a logistics curve is being referred to here, and you might plot this graph on your graphing calculator and have a look at it. A logistics curve takes on this kind of property. It generally looks something like this. You see, where you have that population of fish is going to increase to a certain point until the fish maybe feed out their food supply, and then it'll kind of level off. First question is asking us about that level off point. It's saying, what is the limiting size of the fish population? And the limiting size of the fish population is found by taking the limit as T approaches infinity of this fraction of 10,000 over 1 plus 19e to the negative t over 5. Now think about what happens as t gets larger and larger and larger. Now understand this e to the negative t over 5 means that this right here is 1 over e to the t over 5. And as t gets big, this denominator gets very large, and so the fraction itself approaches 0. So this then is approaching 0 as t gets infinitely large. And as this approaches 0, 19 times 0 is 0, so we have 1 in the denominator. So the population limit is 10,000 according to this logistics curve formula. Next question says, at what rates is the fish population changing at the end of 1 month and at the end of 10 months? At what rates is the fish population changing? Well, when we start talking about rate of change, we think immediately about derivative. So we need to take the derivative of P of T. Now, P of T is this, and I'll rewrite it as 10,000 times the denominator to the negative 1 power. It might make it a little easier to think about. Now, the derivative of this means that we want 10,000 times the derivative of that. So it's 10,000 times the derivative of this. And we have to kind of use the chain rule twice here. It turns out that it's, well, let's see, we think of this as a single entity. So it's the derivative of that single entity to the negative 1 times the derivative of the single entity. So it's negative 1 times single entity to the negative 2, and then times the derivative of this. Well, the derivative of this is, the derivative of 1 is out of here. The derivative of 19e to the negative t over 5 is, let's see, it's 19e to the negative t over 5 times the derivative of this. It's the e to the u idea, you see. And this is negative 1/5 t, so the derivative of that is negative 1/5. Okay, so we have all of this string of factors, and we could leave this string of factors just as they are, or we could clean it up a little bit. Now, if we're doing the work by hand, we would probably want to clean it up. If we're putting the information in the calculator doesn't care how complicated it looks, so it doesn't make too much difference. If you try to clean it up a little bit, you might notice you have negative here and negative here, so those negatives go out. We have 1/5, we have 19, and we have 10,000. So I can think of the 19 over 5 times 10,000, you see, just dealing with those constants. And then for the rest of it, let's see, we have the e to the negative t over 5 can be thought of as moving to the denominator like this. And this binomial raised to the negative 2 can be thought of in the denominator squared. So that's a way of working with it. There are many other ways, about a gazillion of them, to manipulate this into other forms. Well, let's see, I've repeated the problem up here, and I've consolidated the 10,000 times 19 over 5 as 38,000, and those two factors in the denominator are here. Now, to find out the rate of change at the end of 1 month, we find p prime of 1. Now, I'm not showing all of the steps here, but replace t with 1 here, and punch the calculator, and we find approximately 113.5 fish per month. That's the rate of change in the population at the end of 1 month. At the end of 10 months, we replace the t's with 10s, punch the calculator, and we find 403.2 fish per month. So the rate of change in population is increasing, and that rate increases for a while. If you think about that logistics curve, I mean, it's the curve is doing this, and then it goes up and levels off. Now, so right in this region, and I'm overemphasizing it a little bit here, but that rate of increase is increasing and increasing and increasing. That rate of change is increasing up to, a point somewhere in this neighborhood where we have kind of an inflection situation, and then it begins to level off a little bit later. The next question here related to this increase situation is, after how many months is the population increasing most rapidly? After how many months is the population increasing most rapidly? Now, come back over here and look at the graph. Graphically, we're looking at that spot where our tangent line would be steepest. The slope of the tangent line would be steepest. And when is it as steep as it's going to get? You see, at what point? And that is what we're looking for. We're looking for a time associated with that. Now, another way to view the situation is to think of this part of the problem as one where we're saying, when does the acceleration of growth level off? When does the acceleration of growth in population become zero? Now remember that we began with a population function, and then p prime of t is a rate of change in population function, and p double prime of t then would be an acceleration function. So we would have a function of acceleration if we calculate p double prime of t. Now, I'm not going to show you the steps involved in this process. I'm confident that you can do this. It's a little bit thick, but this is the answer to that. This is p double prime of t. Now, we want the place where we want the t such that this second derivative function becomes 0. The 0 of the second degree function will be the well, there's several interpretations here. I'm not going to try to interpret too many ways here because it can get a little bit too complicated. But we want to know where that acceleration becomes 0. That's a good way to think about it. So we want to set this equal to 0 and then solve it for t. Well, when we set it equal to 0, if I just put equal 0 out here, look at the nice things that happen. I can multiply on both sides by 5, and this 5 goes out. I can divide on both sides by negative 38,000, and this goes out. Now, this with this negative exponent, this is 1 over e to the t over 5. So I can multiply on both sides by e to the t over 5 and get a cancellation here to 1, and then over there it just goes out. And in a similar way, I can multiply by this denominator on both sides, and this will cancel, leaving 1, and on the other side 0. So all I have is the 1 minus 19e to the negative t over 5 set equal to 0. So I have 1 minus 19e to the negative t over 5 equals 0. And now I can separate these two. I'll add the 19e to the negative t over 5 on both sides and get this. Now the e to the negative t over 5 is 1 over e to the t over 5. And now multiplying by that on both sides, it's beginning to clean up rather nicely, isn't it? I have e to the t over 5 equals 19. Take the natural log on both sides, and this t over 5 becomes the coefficient of ln e, which is 1. So it's t over 5 equals ln 19. And this is the part that becomes 1. And now to solve for t, multiply on both sides by 5. We find t to be 5 ln 19, or t is 14.72 months. So this acceleration of growth stops at 14.72 months.